Hello, hello, hello. Welcome back, guys. It is Thursday, the 20th of August, and today we're going to be going through a bunch of TMUA Paper 2 logic. First of all, apologies for not being around last week. I had when I say crazy life admin, I mean it's the sort of thing where you get the call and you're like, oh, this week has changed now. Like, this is very much not what I thought I was going to be doing. Everything I thought out the window. There will be no streaming. There will be no nothing. There will be sorting out this issue. So apologies that didn't happen. Normally, I very much like to stream every single week. So sorry off the bat. If you are new here, reminder that the sort of way this works, I do live tutoring to the internet. If you show up and get in my chat, you get some free tutoring. That's how it works. There's also a Discord server where you can make streaming suggestions. Until January, I think I'm very much going to stay on the ESAT and TMUA stuff. I know that there's like R2Drew2 for doing some TMUA stuff, like how to do the actual questions. One thing I can do, though, to really add to things is go through the exam technique. How do you do the strategies, all that kind of stuff. So today I have in the Discord, sorry, I'm looking at my second screen now. In the Discord server, someone suggested yesterday that I go through some paper 2 stuff, the necessary and sufficient logic, if and only if logic, and how to kind of get around those questions, doing some examples of how I use my techniques. Now, interesting thing about my background, I'm much more of like a science background. So I did natural sciences at Cambridge. It included math, but I don't have like that same sort of pure math background that some people have. So if you're looking for like the strict pure math thing, then I'm not your guy. But what I can do is make sense of stuff. So when I was first trying out paper 2 stuff, it was just like diabolically difficult in that I like hadn't done it before. So I just didn't know what I was doing. So I had to come up with systems that worked for me. So if you're more sort of coming into this from like an econ perspective, the way I kind of jerry-rigged it to make sense for my own brain might be helpful if I give it to you, right? So there is a UAT website where they have structured notes on the logic and proof for everything you need for paper 2. I don't do it that way. I do it like my way. My way works for my brain. And I found that it's actually a really neat way of condensing a lot of information in a very simple diagram. So what I'm going to do, first of all, is, having not prepared it, oops, my bad, I'm going to get out my Miro whiteboard. I'm going to show you guys, wow, really haven't prepped. I haven't been in Miro in ages. I'm going to get into the Miro whiteboard and show you guys how I make sense of if and only if questions. Okay. So getting into this, zooming in, I'm going to pop you guys on the second monitor, and we're going to get into it. So here's what I do for the stuff on the logic and proof. And then I'll show you how we use those in action. And then we'll build up to the really difficult problems. So typically, there will be a lot of things they ask you about here. They'll ask you about like, something is necessary for this, something is sufficient for that, if this, then that, only if and only if, what's the contrapositive? All of these statements, and all different statements can mean different statements, and they can kind of all mean the same thing, and it can all be very confusing. So I kind of organize it in what I call mapping. So I like to create the logical mapping that connects conditions in effect. So for instance, let's consider some different statements. So there's typically 3 types of statement you need to consider. If A, then B is the first statement. You've also got B only if A. And then you've got B if and only if A, which I will just write as this I double F. So there's these 3 statements. Now, what I do is I consider the logical links that are allowed to exist between A and B. So A can, in fact, I'm not even going to draw the dots. I'm just going to, so A can be true or false, and B can be true or false. Now, when they're saying if A, then B, they mean if A is true, then B is true. What does not exist is if A is true, then B is false. It makes no constraint on anything else, though. So it makes no statement at all about if A is false. The only thing it's saying is if A, then B. So the only thing it's doing is it's getting rid of that cross term. And in fact, I'm going to stop drawing them like arrows. I'm just going to draw the links between them because those, in fact, go both ways. Now, the reason why I think this representation is helpful is because it contains so much additional information just in the one diagram. So this diagram also contains the information. Well, I mean, first of all, let's rewrite this. This also means that A is sufficient for B, right? So A is sufficient for B. It means if I have A, then I can conclude with certainty I must end up on B being true. But there is other information contained in this diagram. We can also see, because anything that's special in this is something where it only has one line coming to it. So there was only one coming from A true, but there is also only one line coming from B is false. So we can say if B is false, then A is false. And that statement is called the contrapositive. It is the other thing that has to be true. Now, if you want to form the contrapositive, what you can do is take your statement, flip the parts round, and negate them. So flip the round to put B at the front and A at the back, and negate them both. So if not B, then not A. And we can see that is true from here. And we can rewrite that. We can write that not A is necessary for not B. But because these lines work both ways, there are even more statements that come out of this. We can also say if B, sorry, not if B, then A. We can say A only if B. So the only way for A to be true is for B to be true as well. And we can also say that A being false is sufficient, is necessary, and is blah. This is the thing. There's so many statements, guys. We can also say that if not B, well, we've already said if not B, then not A. So B is sufficient. No, B is not sufficient for A. B is necessary for A. God, I always find it difficult to find all of them. So if A, then B. Yeah, it's not B, only if not A is the other one. So the only way to get to not B is through not A. So we can see we have 1, 2, 3, 4 if/only if statements, and they're equivalent in necessary and sufficient. So we have A is sufficient for B, not A is necessary for not B, B is necessary for A, and not B is sufficient for not A. So what we can see is that there are 8 statements here, 8 different logical statements that I have managed to condense into a single Z-shaped graph, which is why I find the sense of logical mapping extremely helpful, because it tells you not just the first thing, it tells you the other 7 in a simple to understand diagram. So if we kind of show you what that looks like for B only if A. So again, let's consider the logical mapping, logical pathways that are allowed to exist between the true and the false. So B only if A. The only way to arrive at B being true is if A is true. So that connection exists. The connection does not exist between A being false and B being true. The only way to get to B true is through A true. It makes no restrictions on B false, though. So the others are allowed to exist. And we can see we have this other shape. The first one was this nice Z shape. This one is it kind of reflected. And you can consider what all the other statements are. So the other statements might be, so B only if A. We can say, B is sufficient for A. We can say, if B, then A. We can say A is necessary for B. And then we can do the same with the falses. So we can get the contrapositive, which is not A only if not B. We can say that not A is sufficient for not B. We can say that not B is necessary for not A. We can say not, well, we've already said not A only if not B. See, it's, where's the other one? Oh, man, I like it's so tricky. This is what I mean. Like pure logic is very difficult for most brains to get around, which is why I just like this mapping, because it has all 8 statements in one. 1, 2, 3, 4, 5, 6, 7. I'm missing one. It's an not A only if not B. So is it a backwards one? No. So not A only if thingy. Oh, it's if not A. There we go. If not A, then not B. So kind of going forwards and backwards along these lines. If and only if is probably the easiest, because now let me show you as well. Let's go back a bit. Let's sort of see how I got these different 8 statements out of this mapping graph, right? So what I did was I considered any line that, and let me consider this a different way. Let's consider any point which only has one line coming to or from it. So that would be A true is a point with only one line coming from it. Means, and let's describe what that line is saying. That line is saying if A, then B. It is saying if I have B, then the only thing I'm going to get, sorry, B is necessary. The only way to get to A is from B. Another way of saying that is A only if B. So going forwards, it's if A, then B. Going backwards, it's B only if A. Sorry, A only if B. Gah! This is why we map it, so we don't have to think about how to say it. This is what I mean. If you're a pure math bro, I am not the one for you. But if you are everyone else sort of trying to make sense of this and trying to just jerry-rig it, I will show you how this mapping is just like absolute chef's kiss perfection. But that's what you're doing. You're looking at any point which only has one line coming to or from it. So here, B, if and only if A. So given that you can see that I am a person for whom this is not the super intuitive, let me show you how I use these mappings to make sense of these questions. So this one is if A, then B, and the only way to get to B is from A, which means there are no cross terms. And we can write out all the equivalent statements, which are basically just the same. A is necessary and sufficient for B. Working forwards and backwards, we can say not A if and only if not B. It's the contrapositive. So, and we can do all the other ones as well for this. So 8 logical statements, all condensing onto the exact same mapping. So if you can get your mapping, you can understand everything that is happening in a situation. Now, how is this useful? So first of all, by understanding what logical pathways exist, you can understand what statement is true. Also, you can work out what instead you can work it the other way around. So if you want to test for a given statement, what you can do is say, if this statement is true, what do I need to be looking for? So classic example I like to use, you can be drinking only if over 18. Over 18, right? So you can be over 18, you can be under 18, you can be drinking, you can be not drinking. So in order not to break the law, what can exist? You can be 18 and drinking, you can be over 18 and not drinking, you can be under 18 and not drinking, but there cannot exist this link between under 18 and drinking. So that is the mapping, is this sort of backwards Z. So what's the test? What we're really testing for is, is anyone under 18 drinking? And we can see what we're really testing for is, does this exist? Because for this statement to be correct, this cross line can't exist. So let me show you that. Now that I've introduced that, let me show you how that works on a few simple questions I've got sort of lined up. What I've done is I just downloaded like all of the TMUA paper twos. I'm going to show you from sort of the basic stuff, how I use this idea of mapping to apply to some easier questions, and then we'll build up and I'll show you how to deal with some monstrous questions. So let me switch screens for a second. We're going to do not the entire screen. We're going to do window, this window instead. Let's take it from, so there's just a few easier ones. So 2016. Now, hold on. A spoiler alert is in effect. I'm about to start sharing interesting questions from literally every single TMUA paper 2. I am going to timestamp them down below so you can skip any of the ones you want to keep fresh. This is a spoiler alert, and if you want to do them live, unseen, please do not watch the rest of this. So obviously, like, you can burn through and it can spoil it as a sort of test run for you. But I am going to start going through them, just to sort of demonstrate. Spoiler alerts down below. I mean, obviously not if you're watching live. If you guys are in chat and you want to say something, if you want to tell me like, hey, don't do a specific year, maybe I'll like avoid it. But in the meantime. All right, so let's use this idea. This is a nice warm-up question. Which of the following is sufficient to conclude this? So we're going to have a condition, which is going to be true or false. And either x is less than y, well, that's either going to be true or false. For it to be sufficient, if it's sufficiency mapping, it is, if you start there, it is sufficient to say that you end up there. Meaning if you start there, you don't go anywhere else. And this is your mapping. This is the sufficiency mapping. There's only 3 possible mappings if you sort of arrange them correctly. So that's this one. So what's the test? What is it really saying? What it's really saying is, can the condition be true? And you have x is bigger than y. That's the question. That's what this simplifies to. So you can use the idea of mapping to simplify the question to make your life a lot easier. So here, can you ever get a case where the statement is true and x is actually bigger? So in the first instance, it's sufficient to conclude that this x must be less than y. So what you got to do now is sort of come up with your counterexamples. So for instance, here, because there's to the power of 4, we're thinking about positive versus negative. So can x be bigger? Yeah, let's say x is equal to 1, y is equal to -2. In that case, the condition is true, but it is not true that x is less than y. So because that link can exist, this is not sufficient. And B is very obviously not true because you can have, if this would have y equals 1, x equals 1, in which the case x is not less than y. For C, let's consider the 1 over x graph. Okay, so if x is less than, sufficient to conclude that x is less than y. That is not true, because if we had these 2 points, for instance, then here, this to the -1. So if this was x and this was y, so say we had like x equals -1, y equals -2, then it is clear that the condition is true, and yet the statement is false. And D doesn't work for exactly the same reason, sort of intuitively, on this part of the graph. So if x is equal to 1 and y is equal to 2, it breaks. Now, for F, can it be true? So for instance, again, we can use x equals 1, y equals 2. Then E is true. Hold on a minute, I've got myself tongue-tied now. Apologies for that. Let me try this again. So it's sufficient to conclude that. Well, if x is equal to 1 and y is equal to 1, then this condition is true. So I think it's this one, because I think here, if this one's bigger, then I think that means that y is bigger than x. So for instance, in other words, let me flip this around. So if x is equal to 2 and y is equal to 1, that's what I should have done, then the condition is true and x is bigger than y. So it can't be that one. And that's why the answer is E. That's how we can use this idea of mapping to understand the sort of win condition to make our lives easier. So if I hop over now into 2018, so spoilers for 2018 if you don't want that, let me show you how we use it in question 5. So again, these are going to be the warm-ups, and then we're going to kind of get into the main event. So here, 2 diagonals of the quadrilateral 2 are perpendicular. Which of the following statements is necessarily true? So in this case, I actually wouldn't use the idea of mapping, but necessarily true means must be true for the quadrilateral. So given that the 2 diagonals are perpendicular, which of these must be true? So the actual thing you have to ask yourself is, well, in fact, let's use the idea. So the condition, sorry, let's be explicit about the condition. So the diagonals are perpendicular, can be true or false. And then the statement as a result can be true or false. And no, you're right. No, I don't. I think in this case, it's actually, because if it's necessarily true, I think you have a good common sense understanding of this. So here, what I'm thinking is necessarily true means it kind of falls out from it, right? It must be true now that the perpendiculars are, the quadrilateral, the diagonals are perpendicular, right? So if the diagonals are perpendicular, which of these falls out? So one of the diagonals is a line of symmetry. That does not have to be true. For instance, in the case of a rhombus. In the case of a rhombus, the diagonals are perpendicular. Is it a line of symmetry? Let's draw an even better one. Let's draw some like random diagonals and then draw the quadrilateral, right? So those diagonals are perpendicular. Neither of those is a line of symmetry. So one does not have to be true. The midpoints of the sides of the Q. Ew, someone in the comments section says that ESAT Camp is a good website for the mental math part of the ESAT. Also, reminder, ESAT Lab is a good place where you can get free questions. No, honestly, if you're in chat, you're important, right? I very much prioritize the people in chat. So don't worry. But yeah, so if you haven't got onto ESAT Labs yet, get into ESAT Labs because a lot of the stuff for ESAT is paid. Also, the common question. So also unrelated to the question, but should I be doing TMUA paper 2 past papers for ESAT practice? No. It doesn't really prepare you. You don't need this necessary and sufficient logic. What you can do is, however, you can do the TMUA paper 1. Those questions are good for math 2. You can do the ECAA paper 1, which is also good for math 2. And then obviously your GCSE and AS papers at speed would be my best recommendation. So coming back to here, and it's clear in this way. Also, let's say, yeah, so it's very easy to construct one. So I don't think either is necessarily true. I will just check that just in case. So this was 2018. Question 5. Yeah, it's true. That's correct. So the other one from this paper I've highlighted is question 11. So let's get into that. So this kind of if and only if stuff. So we're considering the equation where we have, now graphing is just a top skill for TMUA paper 2, just to make sense of everything. Question. So they said 3 to 4 hours per day. So mental math, working on things like simultaneous equations, quickly, rearranging quickly, simplification of questions, that kind of thing. I'm curious what you mean by they. Who's they who are saying you should do 3 to 4 hours a day? Obviously going to get quite tricky once school starts up again in a couple weeks' time. But it's like ESAT Camp. I will definitely look into that for the mental math side of things. But basically, honestly, I don't know if your Oxbridge admissions webinar guy knows what he's talking about because it also depends it varies person to person. My advice is to go for a no regret strategy. You know how much work you're willing to put in while still having a life, right? Because what the worst case scenario for you is to put in 8 hours a day and do the bare minimum to just scrape in, because that means you then have to do 8 hours a day for the entirety of the degree just to get by. I'm telling you, there's some people who are taking the TMUA and the ESAT who really want a life come September. So I say to those guys, I'm like, all right, well, put in your best bid, right? Put in your bid, like, this is how much work I'm willing to do. If it gets you in, great. And if it doesn't get you in, then you didn't want to go anyway. So that's what I advise, because I think they're assuming that like going to Oxbridge is the best thing for everyone, and it really just isn't, because of like what it demands for your work-life balance, because of the style of teaching. So it's, if you're going for it, like I would say, for me, I would have done a whole lot of work, because for me, the idea of like missing out on a question and not getting in, I would have beat myself up over that for ages. So I would have been doing a lot of work to avoid that, because I would have wanted to avoid any regret. So you just manage your psychology there. Know what you're going for. Do the work that gets you there without the risk of you beating yourself up if it doesn't work. Did I sit an equivalent to the ESAT? No. So back in my day, we had AS papers, which you would sit at the end of year 12. These were proper exam papers that you got your results for on results day. And instead of having like the ESAT or the TMUA, I could present your like my AS papers. I can present my AS results, and they can make their decisions based on that. Ever since they scrapped the AS, that's when in 2016 they introduced these new papers to then have some new metric, right? Because they used to, like, the way it worked. I actually spoke to someone about this when I got in, and apparently, like, not just the grades you got in your AS, but the marks you got in your AS were the best predictor. They were extremely correlated to how well you did in first year. So they were extremely good. But now that they got rid of them, they introduced some new stuff. And so the papers didn't exist. There was a thinking skills assessment, which I had to do to get into some colleges. So I just avoided those colleges because I didn't want to have to take it like an extra barrier between me and getting in. So I was just like, I applied and it was straight to interview. So honestly, you can thank Jeremy Hunt for that. I'm pretty sure he was the one. It might have been Michael Gove. Someone in 2016, whoever the education minister was who got rid of AS papers, blame them. Blame them for you having to like log in and have the website crash the second you're trying to book on to take the test, and then you got nothing left, and then you have to go to 8 a.m. in Basildon. Yeah. The rest are generic advice. Honestly, the ESAT run, like, whatever you can do, whatever I can do to help. If you want to join the Discord server, you want me to do some specific stuff, I'm happy to do specific stuff. Today, we're going to stick to TMUA Day, just because, again, that was requested. And I actually do weirdly have a lot of TMUA students, so I think it's worth getting in and showing how this works. So apologies if this isn't directly related to the ESAT for you, and you want to sort of bail on this one. Most of my stuff is ESAT. This is sort of a rare TMUA one for me, but yeah, I'll definitely catch you at the next one if you don't want to stick around for this one. Also, remember, I've got live solves of like all of the ESAT papers going back to 2016. Hold off on those until you're kind of like ready to look at those. Again, spoiler alert, supply. But right. Also, yeah, keep on those speed runs. Super helpful for ESAT. Right, getting back into how we're going to use the mapping here. So, okay, we have the 2 to the x graph, which is fixed, and then we have a straight line. The equation has a negative real solution only if C is positive. Not even positive, but bigger than 1. The reason why that's relevant is because that's this crossing point here. Well, that's not true. Here, C is less than 1, and I still get a negative real solution. So it's basically trying to come up with the counterexample. For 2, and the way this could have worked is you could have considered your map. So you C less than 1, C bigger than 1, C less than or equal to 1. Yeah. I would say map if you don't understand what's happening. If you do understand what's happening, just do it. So here, the equation has 2 distinct real solutions if C is bigger than 1. Well, that also doesn't have to be true, because if C is bigger than 1, you could have a negative gradient, and then you only have 1 distinct real solution, not 2. So that doesn't have to be true. And then for 3, the equation has 2 distinct positive real solutions if and only if C is bigger than 1. That one I can't see intuitively, so that one I am actually going to explore with the mapping. So C is less than or equal to 1, C is bigger than 1. 2 solutions, true or false, right? So C being less than or equal to 1, C being bigger than 1. So what can I have? Can I have C less than 1 and have 2 solutions? No, because if it was a negative gradient, there's 1 solution. If there's a positive gradient, there's 1 solution. So that does not exist, but that does exist. Can I have C bigger than 1 and have, yes, I can have that. And I can have C bigger than 1 and have 2 solutions, so that exists. So I think it is true that you can have 2 solutions only if, Oh, less than or equals to 1. Oh, that's complete nonsense. Apologies. Should have got there faster. You can tell I didn't have a good sleep day. So we're doing like super chill, relaxed me as opposed to like super professional me. So I'm going to be making a bit of mistakes, but this is how. Yeah, no, that's complete nonsense. So I think the answer is A, and this is why I have the mark scheme on hand, just in case. So for 2018, yeah, that's correct. So the next warm-up one I have is 2019, question 5. Okay, so here, consider the following statements about positive integers a, b, and n, the condition, and the results. So either n divides a or n divides b, and the result is n divides ab. So this sort of vertical line is a sort of, it's from pure math. So that can be true, false, that can be true, false. So these are all the possibilities. So let's work out what logical pathways exists. If n divides a or n divides b, then we do know that it is true that n divides ab. And we know if n divides neither, it could not divide ab, but it could still divide ab. It is possible. So for instance, let's take the case where let's take the case where a is equal to 4 and b is equal to 6. Then 24 is divisible by 12, even though 12 does not divide 4 or 6. So that can exist, but this one can't exist. So now, okay, so we've established all the logical pathways that exist. So now what is that? That means that the condition is sufficient but not necessary, which is B. So it just means I can kind of have everything on paper so I don't have to include it in my head, given that this stuff isn't as natural to me. So this is my kind of engineering sort of workaround here. The other one so 2019 is quite a good paper for this sort of warm-up idea. So we can do the same thing here. Which of the following is a necessary but not sufficient condition? So the condition is either true or false. And it can be a parallelogram or not a parallelogram. Okay. So we want it. So this is the other way around. So in the previous one, what we did was we worked out what logical pathways exist and then worked out what the statement had to be. Here, we want to fit a statement and we have to work out what condition exists. So here, if we want it to be necessary but not sufficient, it means the only way to get there is through that. But it's not sufficient in that if I start there, I can't guarantee I end up on the parallelogram. So this is my mapping. In other words, what's my test? My test is really in these cross terms. We want to make sure there's two tests here. We want to make sure, can I get from true to false? And to make sure I can't go from false to true. So here, in this first case, PQRS. So let's first get rid of the idea of being necessary. Can the condition be false and I still get a parallelogram? Well, let's think about a parallelogram. So PQ, labeled anti-clockwise. Shouldn't really matter, but I'll stick to what they're saying. So in this case, PQ equals SR and PS is parallel to QR. So true to true certainly exists. Can that be false? So if it is false that these things are equal, then it cannot be true. That it's a parallelogram. Which must be true but is not sufficient. Can it lead to something that's not a parallelogram? Yes. It can lead to a rectangle. So that's A is in the running. B, PQ equals SR and PQ is parallel to SR. So true to true certainly exists. Can it lead anywhere else? Sorry, man. Pop in for the next one. Right. So PQ equals SR. So true to true exists. Can that lead anywhere else? Can I get these two being equal? So these two are equal. These two are parallel. I'm not sure that can go anywhere else. Oh, it can be. It can be a rectangle. So again, that's also in the running. C, if they're all equal, no, that's just not a parallelogram. So that's not necessary, right? The reason why it's not necessary is because that condition can be false and you still get a parallelogram. So PQ equals QS. What? That's nonsense. Oh, PR. Do the diagonals have to be equal? No. That can be false and you still get a parallelogram. So it's either A or B. I remember getting this wrong on the last one. So let's consider. So PQ equals, so the opposite lengths are, oh, right. So let's consider something like this, where these are the trapezium, where these are parallel and the opposites are the same length. So in this case, if I label it from here, PQRS. In this case, PQ equals SR and PS is parallel to QR, and I get a trapezium. So that can go to false. So that's the one that's not sufficient, and I think the answer is A. Right, so that was 2019. Let's go to question 14, which I think is also a good one. So which of these statements is a necessary condition? So again, condition can be true. And we've got P of X increasing. True, false, true, false. What does this mean? If it's a necessary condition, that has to be true in order to get there. The only way to get there is through the condition being true. So this one does not exist, and we get this sort of shape. Apologies, did not mean to put the arrowhead. So that is necessary. So in other words, the question is, can this condition be false and I still get to increasing function in this interval? Now I will note this is a polynomial, not a function, which means it is continuous and has no asymptotes. So it's smooth and continuous, and the only way, so if PA is less than B, can that condition be false and for it to still be increasing? Well, that has to be true. Because if it's increasing in the interval from A to B, then it does have to be true that the value at B has to be bigger than the value at A. 2 is not true. That can be false. So for the gradient at A could be smaller. So for instance, if it's an exponential curve, the gradient is smaller at A than it is at B, but it is still increasing. And the third one does not have to be true because it can be increasing with either concavity or concavity, like however you pronounce that. So In both of those cases, it's not necessary. You can get there another way. The condition can be false, and you can still arrive at it being an increasing function. So I think the answer is B. Just going to check that real quick. Yep. And the other one, oh, that was it for 2019. 2020, I said question 6 and 7 are ways of introducing this. So here, again, necessary and sufficient. Which of the following is necessary to ensure? So again, reminding yourself what necessary looks like. So we have condition, equation. Both can be true or false. A necessary mapping looks like this. The only way to arrive at the equation being true is through the condition being true. Okay, so the question is, can the condition be false and the equation still be true? Now I've used my mapping to simplify the problem. This becomes a lot easier. Can I have this be true without the condition being true? So what you can do is you can draw some random nonsense and say, trust me, bro, that's -5, that's 5. If area A1 equals area A2, then condition 1 is false, but the thing is still equal. Condition 2 is false, and the thing is still equal. And condition 3 is false, and the thing is still equal. So none of these are necessary. You can arrive at this equation being true without any of these conditions being met. So in this case, the mapping is helpful to simplify the question for you. This is another classic. So which condition is sufficient this time? So we can have a condition, and it can and is it a square? So true, false, true, false. So a sufficiency mapping. If I start there, it's sufficient to conclude I must end there, which means nope. Which means that you don't go from true to anywhere else, and it looks like this. So the question really becomes, can this condition be true and I end up anywhere else other than a square? So in this case, yes, I can end up on a rhombus. Ooh. Sorry, common question is interesting. If I had a degree apprenticeship, would I choose it over uni? No. Like, because also I was like, from the age of 5, I was like, I'm going to be a research scientist until I actually got to university, discovered what research science was, and then went, I don't want any part of that, like at all. So no, I know from where I was in my educational journey at sort of year 13, like I was always going to university. I think what would need to be true in order to make me choose the apprenticeship? If I was going for like very much an applied field. So if I was doing this en route to wanting to be an engineer, electrical engineer, something like that, a mechanic, when I say that, like a sort of car engineer, something like that, then maybe that would make more sense. Maybe something like architecture, that might make more sense. But I think for me, I was too interested in exams and the theory and wanting to just be in uni life. So I definitely would have chosen uni. Obviously, this really depends on the particulars of your situation. So I can't give specific advice. But yeah, that's what I'd say about that. So going back into this real quick. Hopefully that, yeah, nice. So coming back into here, we're really asking, can the condition be true? And you end up on something that's not a square. For 2, yes, you can also get a rhombus where the diagonals are perpendicular. And if those angles are equal, it can be a rectangle. So none of those is sufficient. Going into 2021, which is another good one to really sort of warm up these skills. And I think it's worth really demonstrating these so that like they're locked in by the time we get to the hard stuff. So here, which are necessary conditions? So you have the condition, probability equals 4/15. That can be true, false. That can be true, false. We want it to be necessary. So we want The only way to arrive there to be through the condition. So we want this mapping. What does that mean the test is? The test is, can you get to the probability being 4/15 any other way without the condition being true? So the first one, can that be false and you still get a probability of 4/15? Yes, because that could have been 8 out of 30, which means that 22 students do not wear glasses. That is not a necessary condition. The number of students in the class is divisible by 3. Well, it has to be out of 15. It has to be, so we can scale this up. So it can be 4x over 15x. But that does have to be true. If so that's what we did here. We said x is equal to 2 got us to 8 over 30. That's how we knew you didn't need exactly 11 students. But in order to simplify, remember, it's the probability is the desired outcomes over the possible outcomes. And it has to simplify such that the number of possible outcomes has to be a multiple of 15. So therefore, it also has to be a multiple of 3. Like, that does have to be true. Well, 3 does not have to be true. That condition could be false. There could be 15 students, 4 of whom wear glasses. So 2 only is my answer there. I'm just going to quickly look that up just to make sure I didn't do any silliness, but I don't think I did. 3, yep, perfect. I've noted question 6. Cool. Consider the following 2 statements. Okay, so this is one where you have to work out what that mapping is. So let's consider, luckily they've already labeled them P and Q, so I'll just keep that same label. True, false, true, false. Okay, so let's consider the most basic case. F of x equals 0 for exactly 3 real solutions. There's 2 turning points. So true to true exists. False to false. Straight line. P is false, Q is false. So false to false exists. Let's consider these cross terms. Can you have 2 turning points? Yes. So false to true exists because of a cubic which goes like this. Then Q is true, that there are 2 real values of x for which their the gradient is 0. But here it is false that there are 3 real values of x for which the function is 0. So therefore that connection exists. Final one we have to test. Can P be true and Q be false? Can we have, yes, that is definitely true. So we can, for instance, have something like that, some sort of quintic, which has 3 real solutions, but more than 2 turning points. So actually, it is neither necessary nor sufficient. It is not interesting. There's no point, which only has 1 line coming from it. And that's why the answer is D. Question 8. Okay. So, and then you can see, by the way, I'm doing a lot of this it's a sort of robust system. So I can kind of lean on that so for right now I've got tired brain where I'm like not into the real deep thinking of it all. Apologies, pure mathematicians. So I'm like, all right, I'll just throw it in the system and the system works. And so it's useful for that, right? Which means it's going to be more robust technique for you to use in the stress of an actual TMUA. So here, question 8. Consider the following statement about the polynomial. Which of the following is true? So again, we want the condition. So PA equals PB. Can be true or false. And then we have the statement, which can be true or false. So let's work out what exists. So here, so the condition, and then this. There exists a number C between A and B such that the gradient is 0. Okay. So, and it's a polynomial, not a function, which again really matters because it means it must be smooth and continuous with no breaks or asymptotes. So I think it is certainly, it can, so if the values are equal, there can be a turning point in between. True to true exists. If they are not equal, there could not be a turning point in between. That false to false exists. You can have a turning point in between, but these values not be equal, as is the case with this, for instance. So that exists. I'm not sure. I think I am not convinced that true to false exists. I think for it to be a polynomial, with any two things being the same, the only way that can work is if it turned around and came back, or it could have been flat, in which case the gradient is always 0. So I think true to false does not exist, and I think it is a sufficient but not necessary condition based on that mapping. 9, we can use it. So here, consider the following statements about a polynomial. Again, a polynomial, not function. Let me mark off the ones I've done. Cool. So, okay. So we've got this cubic. There's a real number t for which it's a turning point or the gradient is 0. Which of the statements are sufficient to have a real solution? So the statement, and we can have f of x equaling 0. We want a sufficiency mapping, which means that goes only to true and it does not go to false, which means that's what we're asking. Can the statement be true and you end up having this not be true? So 1, if it's a cubic, we can guarantee that it has a real solution because a cubic will always go just for sort of from the end behavior, we know it's going to shoot down for minus. When x tends to minus infinity, it doesn't matter whether p is not positive or negative. At some point, it's going to have to go through 0. So if statement 1 is true, it is definitely true that there is a real solution. Okay, so there's a real number t for which the turning point is 0. That, I can have that be true and not have, for instance, a quadratic with a turning point above the x-axis would not have a real solution to f of x equals 0. So 2 does not have to be true. I can get from statement being true to equation being false. There are real numbers for which, now, okay, so when you see this, f of u times f of v must be less than 0. The only way that's positive is if 1 is positive and 1 is negative. And again, we're talking about a polynomial, not a function. So if 1 is positive and 1 is negative and is continuous in between, then somewhere in between, it does have to go through 0. And that is, so that is true. If that is true, the only thing that can be true is that f of x equals 0. So so it's yes, no, yes, which is C. All right, let me just check that. Yep, perfect. So that's crossed off. Now we just got a couple more before we get into some more advanced techniques. 2022, question 6. Again, this is one where we have to work out what the relationship is between P and Q. True, false, true, false. So n is odd or n is even. If n is odd, the median of the list is one of the numbers in the list. That is always true. And we know you cannot go from true to false. If n is odd, the middle number is the median. So that is true. And we know if you have an even number, the median can be one of the numbers in the list, but it could not. So that means that that is sufficient, but not necessary, because that's what that mapping looks like. And finally, 2023, question 5. So consider the two statements. Which of the following statements is true? And again, this is one where we have to establish the pathing. True, false, true, false. So k is an integer number of pi. Well, let's actually do this integral, right? So integrating, so that you would get minus a half cos 2x between k and 0, minus a half cos 2k plus a half equals 0, which means that cos 2k equals 1, which means that 2k is equal to 2n pi, which means that k is equal to n pi. So I certainly think if k is equal to n pi, so true goes to true. I don't think true goes to false. False goes to false. Can you get this integral equaling 0 even if it's not an integer number of pi? No, because I think we just worked backwards. We said in order, this is what we just said, in order for this to be true, nk, so I think it is necessary and sufficient. So I think it's A. So 23, answer key, question 5, A, perfect. So those are my warm-up ones. That's how I use necessary and sufficient. Let me just check on some of these more complicated ones to see, because I know there's a mix. Some of them are like if and only if, or some of them are just wild. So this one is wild. I'll do that later. Here, question 10. I noted down. Yeah, so this one's, we're now going to level up in difficulty a bit. So again, which is a sufficient condition. So you know what to do. We have condition, we have equation. True, false, true, false. Sufficiency, true goes to false, true does not go anywhere else. So we want that. So what is the question? What's the test? Can the condition be true and you lead to the equation being false? So can this be true and this integral is not 0? Yes. I can draw something like this where that is 2, and we can integrate between 1 and 3 and you would not get 0. Can this be true? Yes. So if I did something like that where that was 1 and that was 3, the integral between 1 and 3 would not equal 0. For C, can that be true? Yes. Let's consider x cubed. The condition is true for x cubed, and the integral between 1 and 3, not 0. Now, this is where stuff gets a little bit fun. And this gets harder specifically because of what these conditions mean for the graphs. But in this case, it's sort of this even and odd idea. But in order for this thing to be 0, we would kind of want it to be symmetric about x equals 2. Because then between 1 and 3, that would cancel out perfectly. So in other words, we want f of x minus 2 to be the negative of f of 2 minus x, which is that times the minus 1. So E is the sufficient condition. If E is true, then you get exactly what I described. But let's say you couldn't get that last step. You could still use this idea of mapping to understand what the test is for sufficiency to at least eliminate 3 of the possibilities, which makes your guess percentage that much higher. So increasing your chances if you have nothing left to sort of go for. So getting rid of that, question 10. 17, I think, was a We'll get onto that. So 18. That's a proof one. Okay, sufficient. So which of these is sufficient condition? Again, condition equation. Sufficient looks like that. So we want to ask, can the condition be true and us have the equation being false? Or no, not the equation, so the exactly one real root. Okay, so can the condition be true and we have no real roots or more than one real root? So first we can understand what this cubic is. So to understand the number of roots of a cubic, this is a very common TMUA strategy. You need to get the turning points and understand where they are relative to the x-axis. So we have a bunch of different possibilities here. One root, that would be 2 roots. That would be 3 roots. That would be 2 roots. That would be 1 root. So if you can understand where the turning points are relative to the x-axis, then you're all good to go. Apologies, I've covered that up with my face there at the bottom right, but I think you can kind of understand what I'm going for. So let's differentiate. So x equals 0, x equals 2. When we plug in x equals 0, so we have the turning points are at 0a, and we plug in 2, we get, this would be 8 minus 12 is minus 4, so we get 2 and a minus 4. Okay, so here's what we need to have exactly one real root. We either need a to be less than 0, or we need this minimum point here with a y coordinate of a minus 4 to be bigger than 0, which means that a is bigger than 4. So these are the necessary conditions. These are the things that must be true. So if these things are not met, it does not arrive at one real root in order to be sufficient in the first place. So a bigger than 0 does not count. A equaling 0 does not count. You would get 2 roots. A being bigger than or equal to 4 does not count. A equals 4 gets you 2 roots. A being less than 4 does not count because you can get anything in between. Here, h does not count because and then a is not bigger than 4. Here, a equaling 9 over 14. Sorry, equal 9 over 4. That is 2 point something, does not count. A is not bigger than 4. Here, modulus of a being less than or equal to, nope, because we can get a equals 1 would count. So the answer is E, because what that means is that a is less than minus 4 or a is bigger than 4, both of which are included in what we need. So that is the sufficient. If this is true, that arrives at one real root. There are other ways of getting one real root, which is anything included between minus 4 and 0, but that is the sufficiency. Okay. So going into 2018, question 10. Yeah, let's talk about this. So again, so which of these are necessary and sufficient? So this means 1 to 1, true goes to true, false goes to false. It means they just are the same thing. So for which of these does it mean guaranteed that this has reflection symmetry in the line x equals a? So line x equals a. That means that here, if that's a, what we know is if these distances are, if they're the same distance apart from a, then they have the same value. So what that means, so let's say this is f of x, right? What value is going to have the same value as that? So this distance here is a minus x. So this distance here is a minus x. So it is x plus 2 lots of that distance. So it is x plus 2a minus 2x, so 2a minus x. So that means that f of x equals f of 2a minus x, guaranteed. And now we can do a... Sorry, I just clocked in that there was some new chat. Peace, welcome. What's up, losers? It's literally just you in the chat, sir. So check yourself. Now it's TMUA day. It's a bit quieter. It's what it is. Oh my god, I forgot to apologize for not checking in with you guys last week on A-level results day. Apologies. I think if I remember you from chat, I think you sat your A-levels and it may have been results time for you. So let me know what you got. Right, what we do now, and this will be helpful for you if you end up doing math in your future degree. I know, right? Imagine not having done the A-levels. Literally everyone who's still watching my content because they have the TMUA or the ESAT coming up. So what we can do is we can substitute anything in for x. So they seem to... oh, well, there you go. So that's 2 already necessary and sufficient. Ding, that's in. Now let's see what happens. Well, 3 can't be right because f of x has to go with 2a minus x. Let's substitute x with a minus x. So f of a minus x on this side would equal to f of 2a minus a plus x. So x plus a, which is 1. So it's 1 and 2. So it's yes, yes, no, which is b. Let me check. So 2018. Answer key, is it B? For question 10, yes it is. So that one was more complicated, more from the math perspective than the necessary and sufficient stuff. But that's how that works there. All right, I'm looking at 12 a monster, or is it? No, okay. So that's, we'll come back to that. Where was 2016 question 7? Oh, that was this one. That was Rogue. Cool, fair. 2019 question 17 looks bad. Oh no, we'll get onto those. This is coming. I'm going to have a whole separate section on this. So 2020 question 12. Okay. So here, the trapezium rule produces an overestimate. So let's talk about overestimate, underestimate. I think I've talked about this in a previous stream. But the idea here, you can have different types of curve. Sort of, I like to think of them based on a circle. Oh, sorry, that's not great. Doing that and doing that. So if we have this, then the trapezium would be an underestimate on both of them, actually, because the lines of the trapezia that you would approximate this to lie under the curve. So these are both underestimates, and these will both be overestimates because the lines approximating the curve lie above the line, go over the line. So the trapezium rule produces an overestimate. Let's see. So gradient positive, and the gradients are decreasing. That is this first case. That produces an underestimate. No. Actually, do you know what I'm going to do? I'm going to use mapping here. So we're going to, because it's only really talking about, so we either have, we have gradient positive or gradient negative. And then we have second derivative positive versus second derivative negative. So Also, hi, you in the chat, you are new to this stream. So I'm in one of my moods where I'm like super not sleep goodly and therefore just like zombified. So we're doing chill and lazy today, and that's fine. So let's work out what actually exists to be an overestimate. So an overestimate, gradient can be positive, and that can be positive. TMA paper 2 is more stressful and effortful, not chill and lazy, which is why you come up with techniques that allow you to do it in a chill and lazy way. You see, that's the secret. So here, overestimate. The gradient is negative, but again, so that we want these two. So all we need really, ESAT's still more difficult. ESAT's, well, I mean, they're just different. They're different. So ESAT, I don't know, they're different. They work different parts of your brain. So basically what we need is the second derivative to be positive. So only if, so that anything where the second derivative is negative, we can eliminate. Second derivative positive, cool. D does not work. Oh, maybe it does work. Well, it's certainly not only if, because you can get there from both perspectives. So it's not E. And it's certainly not if and only if. I think it's D. So as long it's if, but there's no restriction on that being the only case, because you can also get there if the gradient is positive and the second derivative is positive. So you can see this is our first instance of a non-standard mapping. Different. Okay, so different. ESAT and TMUA are different in different ways. So like ESAT is the power is in just go on the very. It's back endy. It's back end difficult. So it's stuff that you've like mastered from the syllabus, but the difficulty is in executing it power. It's like a sprint. Whereas TMUA is more of a game of chess. It's front end difficult, where you have to really think about how to do it, like if you're going to be able to get over the line. So the ESAT, the challenge is, can you make it in time accurately? TMUA is, can you make it at all? sorry for the, yeah, you had to be there. Chat is chatting. I enjoy the chat. 2021, question 11 looks tricky. No, that's logic. All right, so by logic, I meant proof. Year 17, again, that's proof. And here 13. Okay, so now I want to get into these. I want to get into the ones where they overlap. So 2019, yeah, so there's a certain subsection of these where they're overlapping statements. Now, the way to test for overlapping statements, first of all, just as a rule, map them all, and then you can see where my technique really starts to come in handy. So this will be very, very much timestamped down below. So maybe not this one. This one's really ugly. I'll start with this one. Then I'll show you the mapping in a different one. So okay, I'm going to first consider x is bigger than 2, and then the statement. True, false, true, false. Given that exactly one is correct. So let's consider what these mappings would be in these different cases. This would look, so if this, then statement true would look like that. And you would not have this cross one, but you would have this. It would be this kind of Z shape. If and only if would look like this. Yeah, I remember this one trips me out because of like what happens when it's in between 1 and 2. So because here, okay, no, we can still do it on this mapping because some of this gets in from false to true. True to true also works. False to false works. And then here, if x is bigger than 1, which includes some of the false, so both of those can exist. and then that. So my thing is, on this mapping, A, B, and D end up being the same thing. The main thing is that C is the most restrictive one, and C is the one that I can superimpose without introducing a forbidden link. So if I were to impose C on A, it would just overlap already existing links, which means if C is true, then A is also true, which is why it actually can't be C. Is that right? I always trip up on this question. This is where we're getting into the really hard stuff now. Okay, so B includes D. If it's true when x equals 1, well, that includes all of x bigger than 2. So if B were the correct statement, then D would have to be correct as well. If A were the correct statement, then D would have to be correct as well. So D is the one that is only one of the correct options. I think this would best be done on a different example, though. I feel like this was a bad example to start on. I think it's going to work better on 2020. Question 20. So here, let's consider this. So we have a real number and a function. What we have here, let's consider what we're considering. X is bigger than or equal to 0. X is less than 0. We have f of x bigger than or equal to 0, f of x less than 0. Now let's consider what the mappings would be in these different cases, right? And you'll realize that a lot of these are the same thing, which is this is the one that's going to really prove why my technique works. So if this statement is true, what would the mapping look like? The only way to arrive at this being positive is through there. So that exists, that does not exist, the others are unrestricted. So it looks like this weird mapping. X is less than 0 if that. So if you start there, you end there, you do not go there. So these end up being the same mapping. C. This thing is only if that. So the only way to arrive there is through there. So that exists. That does not exist. You get a Z shape. D. F of x is less than 0 if that. So the only way of getting, so if that, sorry, starting there, you only go there, you don't go up. This one. F of only if, so the only way of arriving at top right is from top left. So you can do that, but you can't do that. You can do that. F, if and only if is an X shape by mine. So what you'll see is that D and E end up being the exact same thing. A and B end up being exactly the same thing. Now we have this again, this idea of superimposing. So the answer is not F. The reason why the answer is not F is because you can superimpose F onto A and B and it would still work. So in other words, if this was the truth, how do I explain this? So you can kind of like, if you imposed F on A and B, you would not introduce any forbidden pathway. Obviously, if you imposed it on C, D, or E, you would introduce a forbidden pathway. But introducing it on A and B would not introduce anything new. And so if F was true, that's my clear way of seeing that A and B could also be true. And so the answer is an F. The reason why it's C is because if I try and impose C on any other one, I am guaranteed going to introduce a forbidden pathway. If I try and impose it on A, I'd introduce the forbidden pathway going top to top. Same thing on B, I would introduce top to top, which is forbidden. On D, I would introduce bottom to top, which is forbidden. On E, I would introduce bottom to top, which is forbidden. Here I would introduce top to bottom and bottom to bottom, which is forbidden. So C is the one that does not fit onto any of the other mappings, and so that is the odd one out. And that's the one that is exactly one. Because so realistically, this idea of mapping and which ones fit on top of the other ones neatly can help you with this idea of whether it's exactly one true or not. And that is my sort of cool sort of engineering jerry-rigged solution for that problem type, and I'm very proud of it. Wait for someone in the comments to tell me it's complete nonsense. 2023. Okay, so let's try this. This is going to be a bit more tricky because it's going to be for exactly 3 rather than all of them. And again, this is actually going to be more similar to the previous one. So sufficient. So which ones of these would satisfy the others as well? Is a sufficient condition for exactly 3 of the 4 statements. So sufficient. So B, let's think about this. So let's consider B because it looks like the easiest one to consider. If it's B, that also satisfies C, and it also satisfies D, and it also satisfies E, and it also satisfies A. So B satisfies everything. So if X equals 1, that satisfies everything, and it's not that. C, I'm liking. C satisfies A, I think. Oh, is this where my brain breaks? You see, this is where you actually have to start thinking about it. And I don't think my mapping works as well for this. Let me think. Well, no, actually, what we can do is we can use that idea of mapping it onto the other. So let me draw number lines for all of these. So this is that's the first one. That's the second one. Actually, okay, here's how I'm going to do this. I'm going to draw a number line. There's going to be a 0, and there is going to be a 1, and I should not have drawn it there, but it's fine. So, no, in fact, I will move it. So here's what I'm going to do. Number line, 0, 1. A includes 0 and above. B includes 1 and 1 only. C includes 0 and 1 as solutions. So either X. Well, this is utter nonsense because it includes D includes literally everything. Actually, these are unfilled because they're ors. In a way. So it doesn't have to be either of them. Either has to be included. Yeah, actually, this one includes literally everything because it's those two at the same time. And this one is at least restrictive, where it says you have to be in between. So B lies on all of them, so it's not that one. I think it's C, because C lies on all the other 3 number lines. I like that. E lies on the other 2. So I think the answer is C. I'm going to go with that for 13. Although I am going to look it up because I'm not confident. It wasn't, I looked it up. I thought it would be similar. It's not that similar. It is correct. It is C. I should look up the work solutions for that though, just to be certain. So for 13, so for the first one, B could be false, C could be false, I still don't maintain that I think that's wrong. D can't be false. Okay, so A doesn't work because the others can all be false. Because there can be a solution on here which doesn't satisfy the others. So here, for instance, here, if I had on E, if that was my solution on there, it could satisfy the other two, but it also could not. Whereas here, if I had C, that would 100% like it must satisfy three of the others. Not explaining it super well. That one's just tricky. Apologies. The method wasn't as robust on that one. But I want to show you one. It's on a paper that someone sent me. It's unofficial, so I'm going to be like, nah. But okay, so basically what they're saying is, given that exactly one of these statements is true, which one is it? So it's another which one. So if and only if A is bigger than B, that's one of them. We have this. We have only if A is less than B. We have f of A is less than f of B if A is bigger than or equal to B. We have A is bigger than or equal to B if f of A is bigger than or equal to f of B. A is less than B only if f of A bigger than f of B. A less than B only if f of A less than f of B. Right. So here, let me make sure you're able to see what I'm doing. What this is a relationship between A bigger than or equal to B, A less than B, and the functions, the function values. Right. Let's work out what these mappings would be in all 6 of these cases. If and only if would look like this. But let me kind of do it so they can all kind of superimpose. So this would look like just 2 parallel lines. This. So only if that. So you can only get there if there. So this. So the top line does not exist, but everything else does. So here. I didn't mean that. I meant F of B. Cool. So for C, this thing, so if this, then that. So this only goes there. It does not go across. Same mapping. Look at that. That means these end up being the same thing. A bigger than B if that. So if that, then that. So that exists. That does not exist. So it looks like this. A is less than B only if. So the only way of arriving there is from there. So I can go there, but I cannot go there. So it looks like that. A is less than B only if that. So the only way of arriving there. So it looks like that. So you will quickly see that B and C are exactly the same mapping. You will quickly see that D and F are exactly the same mapping. Now we can think about imposing onto any of the others. So we can see that if we impose A onto D or F, you introduce no forbidden links. So it can't be A. If A is true, then D and F are also true. D and F, in other words, contain A. We can see A, these guys are contained within the mappings for E and F. However, E, if you tried to impose that on any of the other 5, you would be introducing a forbidden root. In other words, none of these mappings also contain the shape of E's mapping. So the answer is E. That is how this can work in those really complicated questions. Cool. Now, so that's the sort of necessary and sufficient stuff. This idea of mapping and which mappings contain other mappings to work out which ones are exclusive. So if only one is true, which one is it? That's super weird. This is my like sort of very like, no one taught me how to do this. I kind of just like worked it out. So I'm not sure you'll see anyone else doing it in this way. So maybe it just helps you see it if you're more of a visual person and aren't like me, very good at the like crazy logic of it all. Do I have time now? We're 135 in. I say, let me look. So I've got, let me show you some quickly. I won't necessarily do the full like number line negation logic stuff because I think I've done that before. I've demonstrated that on the channel before, certainly. So you can try and find that. What I will do though are some of these weird logic and proof questions, right? So there's 3 questions on that I want to cover. I say that. Hold on. Where's question 18 here? Oh, that's a proof. So let's start with this because this one's weird. So this is 2016 question 7. So this is more how ideas thread through each other to form a logical through line. So suppose they satisfy this equation. Use some of the lines given to construct a proof. It follows that this thing is true. Okay, so let's start. All of the options start with 1. So let's start with 1. So if x is equal to log a and y is equal to log a of c, then we can say that a to the x equals b, and we can say that a to the y equals c. We can also say that log c of d is equal to x squared, which means that c to the x squared equals d. God, you can tell my brain is tired. I did this so fluently the first time I did it. No, we can do this, guys. Come on, team. So, c to the nonsense. So d is equal to c to the x squared. That is certainly true. So it's going to be 1 then 3, I think. Okay, so let's do that. So d is equal to c to the x squared. And now let's do log b of d equals log b Well, what are they doing now? There's one grouping there. So the next one is from 5, 6, or 7. So, oh, of course, I'm being an idiot. So c is equal to a to the y. So d equals c to the x squared, which means that d is equal to a to the y to the x squared, which is equal to a to the x squared y. So in other words, it goes from 1 to 3 to 5 to 7 Oh, apologies, not to 7, to 9. I mean, 7 is the same as 9. So it's 3, 5, 9. Okay, let me think about the order here. So which ones get me? Let me just try and do it. So I want to get to here. So we want to get these as base B. So it's a to the x to the xy, which is equal to b to the xy. So that's what you want to do. So in other words, we're going from 1 to 3 to 5 to 9 to 7 to 4. 1, 3, 1, 3, 5, 9, 7, 4 is C. That's wild and out. I thought it was worth pointing out. It's kind of standalone. Let's do some proof logic before we wrap. I think the next one on my list, so it's going to be 11 from 2021, is interesting. So this idea is that each line must flow continuously into the next line in order for it to work. So this is attempting to prove that if this thing is true, then there exists a real number such that this thing is true. So let's consider the following attempt. So this is a true statement. So that. What they've done, so let's sort of check this out. Is there an error on line 2, 3, or 4? There is not an error in line 2. That is what happens when you expand that out. There is not an error on line 3. That is what happens when you complete the square. Because this would be x squared plus y squared plus 2xy, which would cancel with the 4xy to give you a minus 2xy overall, right? So there's nothing wrong with line 3. Is there anything wrong with line 4? No, we've just multiplied both sides by x squared y squared. Because it's x squared y squared, we know that has to be positive, so that does not change the sign. There is no issue. So it's not D, E, or F. The problem here, all of this is a very good start point. But what we've proven is that if these things are true, then a squared minus 4b cubed must be bigger than 0. In other words, what we proved is the converse of this statement, which is C. Let me just check that. So 2021, again, I'm not sure. That just didn't feel like the best explanation, but it's the best my brain's gotten this moment. 11 is C. Yes, that is correct. So we've got this thing is true. So what we proved is if this thing is true, then this thing is true. So we proved them the wrong way around. We flipped around the if and then statements, so we proved the converse. So that I just thought was an interesting proof question. The other one, the final one I'm going to go through today, is question 17 here, which is also very interesting. So A and B are non-zero real numbers. Prove that this equation has 3 distinct real roots. Again, very common TMUA skill. If you want to get the number of distinct roots of a cubic, you work out the 2 turning points. If it's 3 distinct real roots, you need the maximum to be above the x-axis. You need the minimum to be below the x-axis. So how'd they go about this? And let's look, and again, this is weird, right? So this is not the usual where is the incorrect line. So here, so we differentiate that as correct in order to find the turning points. They have differentiated correctly. They have factorized correctly. Yes, they have found the 2 turning points. So what do we know? We know this is the first one because A is a non-zero real number. Because it's a positive x cubed, we know the first one. In which case, I think they're saying A has to be negative. But the point here is you will notice that this guy and this guy, if you multiply them together, what they're saying here is it's less than 0. So in other words, these have opposite signs. So we differentiate and find this. Okay, so now if this thing is less than 0, then these things have opposite signs, which is true. And so one of the stationary points is above and one is below. That is a true statement. If the cubic has 3 distinct roots, then one is above and one is below. That is a true statement. Hence this. But the reason why it doesn't work is because we got to here, and that flowed logically into 2. But what you're supposed to do, 2 is supposed to pick up where the 3 is supposed to pick up where 2 leaves off. So we've got to the point where we proved that one of the stationary points is above the x-axis and one is below. So we needed 3 to be stated the other way around. We need to pick it up from there. So look, we solve one, we start here, we get to the point where we have the stationary points. Cool. Now, if we have these stationary points, we can show that if we multiply the y's together, we get something less than 0, so they have opposite signs, so one is above, one is below. Cool. What we should then do is in 3, we should say, therefore, if one of the stationary points is above and one is below, then the cubic has 3 distinct real roots. So the solution is wrong because the student should have shown the converse in step 3, which I thought was just an interesting one to bring to your attention if we're going through the sort of weird stuff that happens in paper 2. So the main thing I wanted to go through today, and the numbers have ticked up slowly as the stream has gone on, so there's more of you than I'm talking to now. But the main thing I've gone through today is my idea of mapping or pathing as it exists when it comes to like the if and only if stuff, how you can create a single sort of conceptual diagram which only includes 2, 3, or 4 lines from which falls out 8 simultaneous statements of logic about the relationships between A and B. So reducing 8 statements onto a very simple diagram can help simplify the logic and free up your brain to do a lot of other things. So we can use that to understand how to test certain statements, test for sufficiency, test for necessity by understanding what forbidden links should exist. We can also test out what different pathways exist to find out what the relationship is. And we could find out in a bunch of simultaneous ones, which one is the only one, if one is true by itself, which one it has to be. So we did that by reducing all of them to their diagrams, working out which diagrams were the same, and therefore they were not unique, they were just the same statement. And then from the ones that were left, do those mappings exist in any of the other diagrams? And so that technique, I think, is the really main one I wanted to go through. You can play with that in your own time, see if you can adapt it, pick it up, work with it. I've gone through negation logic in the past, and those are, I think, the most interesting proof logic questions that I've seen. So hopefully this is a nice comprehensive guide of everything to do with the TMUA. Now, I will timestamp it. Be careful with spoilers. This is certainly one to look into as you've kind of done more of the papers closer to the time. Or if I'll timestamp, and it's gonna be slightly annoying in that the timestamps are gonna be very close together, but I'm gonna put the specific years in it so you can skip between different questions. If, for instance, you've taken 2020 as your cadaver paper, you've already done that to get a sense of what's inside the paper, you can just skip to the 2020 questions so as not to be spoiled from the other papers. And so hopefully you find that this helps you with the revision. Now, probably going back to ESAT stuff for next week. Feel free to drop in the comments of any YouTube video or in the Discord server if you want me to go through something specific. I really like being guided by you guys. It makes my planning and so much easier, especially when it comes to like the interview prep. Like if you guys are active in the chat bringing me stuff, then it like really helps make sure that I can like deliver something that's like most tailor-made for what you need in the moment. So catching me live is always best, and I post when that's going to happen on Discord. Apologies, it's been like I was so expecting this summer to be like super regular, really easy. Like, oh, I'll just do the same time every week. And then just for some reason, I was super booked for the whole of July and then super busy for the whole of August. So it just didn't work out that way. And I apologize. But once people go back to school in a couple of weeks, I think I should be able to get into a more regular rhythm. So hopefully you find that helpful. Now, in the meantime, go off and enjoy the rest of your Thursday. And I will see you guys next week. All right. Take care. See you then. Bye-bye.